show you that this business of finding Nash equilibria and this business of finding subgame perfect Nash equilibria can be very mechanical and procedural if you know what you're doing, okay? And I would like to show you this by making up a game, okay? So let me ask you, so that you're making the game, so I'm not giving you a question that I've kind of pre-prepared for it, okay? I'm just gonna get a completely new game that comes from you, okay? So how many players do you want to have in this game? How many players? 3. Okay, so 3 players. Which player do you want to move first? Which player do you want to move first?
First.
Let's say first player. How many actions do you want that first player to have? 3. Okay, let's do A1, A2, A3. Okay, which player do you want to be here in the first node? Let's say player 2. Which player do you want in this node here? Anyone?
3.
I'd say 3. Which player do you want in this node here?
2 again.
2 again. Okay. How many actions do you want player 2 to have here? How many actions?
2.
Let's say 2. B1, B2. How many actions do you want for player 3 to have? Let's say 2. C1, C2.
2.
How many actions do you want for player 2 to have here? Let's do 2. E1, E2. And let me try and add a bit of complications here. So let's say that here we have player 1, but player 1 doesn't know in which of those nodes it is. So this is an information set for player 1. Let me assume that player 1 now here has 3 options. Here has 3 options. Here the game ends. Here the game ends, ends. Okay? Give me 3 numbers.
5.
I want 3.
1. 3.
5, 1, 3. Okay. Give me another 3 numbers.
6.
Uh-huh.
7, 8.
7, 8. Sure. Another 3 numbers.
2,
Uh-huh.
4, 5.
2, 4, 5. Yeah, another set of 3 numbers.
7, 2, 1.
7, 2, 1. Okay, another set of 3 numbers.
0, 0, negative 3.
0, 0, negative 3. Okay. Another set of 3 numbers. That?
7, 3, 5.
7, 3, 5. Next one.
1, 0, 3.
1, 0, 3. Next one.
8, 1, 7.
8, 1, 7. Okay, 2 more. Next one.
6, 2, minus 2.
6, 2, minus 2. Final one. 2, 8, 3. Okay. We made this game up. Okay? There's nothing special about this game. We completely made it up. Okay? Which means there is no such thing as a difficult game or an easy game if you know exactly the process of going about it. Okay? So I want to show you that this game can be very easily solved if you're following a process on it. Okay? Let's start with something that's going to be relatively easier and a little bit quicker to find out. Let's start with some basic stuff first. How many strategies, how many pure strategies does player 1 have? How many pure strategies does each player have, let's say? Each player have. Let's go. Player 1. How many pure strategies does player 1 have?
3.
Not quite.
9.
2, G3. Player 1 will have 9 strategies. Why 9? Because he can assign 3 possible actions here, and he can assign 3 possible actions in this subgame here. Okay, so he will have 9. Let's give some example of those. For example, A1, G1 would be one. A1, G2 will be the other. A1, G3 could be the other. Right? And how are you going to get 9? Just instead of A1, put A2 or A3, and then you're going to get 3 more of those. Okay, and you're going to get 9 in total. Okay, you had a question.
Yeah, G1, G2, G3.
Yeah.
Does it have to be the same for both C1 and C2? Could it be?
Yes, it has to be the same because the way. So the question was, does this G1 and G2 have to be the same for after C1 has been taken and after C2 has been taken as action? And the answer is yes, because I've put things into an information set.
Oh,
Yeah, this thing means an information set, which means it's also in one of the videos that I've done. I think for question when we talk about question 1, I explain this idea of subgames, but that means that player 3 and player 1 are playing a simultaneous game there. Okay, so I cannot break it up in smaller pieces. Okay, so player 1 will have to just make a decision on G1 or G2 or G3 without knowing in which of those 2 decision nodes he's in. Player 1 will not know whether he's here or whether he's here. That's what that information set tells us. Everybody's with me on this? Okay. How many pure strategies does player 2 have? How many strategies does 4, of course. Why? 2 decision nodes, 2 action at each of those decision nodes. So it's going to be 4. 2 times 2 is going to equal to 4. Let's list them because it's just 4 of them, so we can list them. B1, E1, B1, E2, B2, E1, B2, E2. How many strategies will player 3 have? This is an easy one. How many strategies will player 3 have? 2, of course. In this case, the number of actions will coincide with the number of pure strategies because he only has 1 decision node. So the action for player 3 are going to be C1, or the pure strategies, sorry, for player 3 are going to be C1 and C2. So far so good? Okay, excellent. Now, what I would like to do first is I would like to find first the subgame perfect Nash equilibria. That's going to be my first goal. And after I find the subgame perfect Nash equilibria, I'm going to try and find all the Nash equilibria, okay, of this particular game here, which might be challenging, but we can do it. So let's find the subgame perfect. Actually, I'm just going to focus on the subgame perfect Nash equilibria because the Nash equilibria might be a bit messy with 3 players, right? You have 3 players, so you can't really write it in a normal form game, etc., etc. So just focus on the subgame perfect Nash equilibria. That's going to be more than enough. How many subgames do I have here? How many subgames do I have here?
5.
5, 6, 5. If you look at question 1, there's a point that I've actually defined this idea of subgame, a subgame perfect Nash equilibria, but they need to start from a singleton decision node. So this is 1. This game here will be another one because these other decision nodes here that you have cannot be separated because they're in an information set. So a subgame cannot start from there, okay? Then there will be this. Then there will be the whole game itself. So the whole game itself is also a subgame. So you're going to have here 4 subgames. Okay? So when you find the Nash equilibria, you're going to start to have to do backward induction. Here's where backward induction, let's label them. Let's call this 1, 2, 3, and let's call this 4. The numbering didn't matter. I could have labeled them as I pleased. If you are in the first subgame and you're player 2, what's in your best interest to do? By the way, imagine that these payoffs are player 1, player 2, player 3, okay? If you are player 2, what is in your best interest to do?
B2.
B2. Why B2? 7 is better than 1. So you would want to go down the B2 route. Maybe I can highlight that in red. This is what you want to do as player 2. Okay, what if you are in the third subset? What do you want to do? E2. This is also easy. Now, a subgame perfect Nash equilibria leads to a Nash equilibria in every subgame. So it's a profile of strategies that leads to Nash equilibria in every subgame. So what are the Nash equilibria? So if you think about it, this is a bit, if you look at subgame 1 or subgame 2, you can think of it, even though it's a little bit silly to think of it that way, that B2 is a Nash equilibria in this subgame because the only player, player 2, does not have an incentive to unilaterally deviate in that particular subgame when they play B2. Now, how do you go about finding all the Nash equilibria of the second subgame? How do you go about finding all the Nash equilibria of the second subgame? The answer is you have to think normal form game because it's happening simultaneously. So in that third subgame, you have player 1 that has option G1, G2, G3, and you have player 3 that has option C1 and C2. We're only going to focus on player 3 and player 1 payoff. So player 1's payoff are all these bits here. Player 1's payoff. Player 3 payoffs are all these bits here. Player 3 payoffs. So if GC1 is taken, the payoffs are going to be 2, 5. If C1 G2 is taken, the payoff are going to be 7, 1, 0, minus 3. What about here? C2 is taken, G1, we're going to have 7, 5. Here we're going to have 1, 3. And here we're going to have 8, 7. Okay? And then I can do my usual thing. If player 3 does C1, what is in my best interest to do? G2. If player 3 does C2, what is in my best interest to do? G3. If player 1 does G1, what is in the best interest of player 3 to do? Is C2. Here is this. Here is this. So there is a unique Nash equilibria, G3, C2. That is the only profile of strategies that would lead to a Nash equilibria in that subgame, so I highlight them. C2, G3. I go up one stage, and now that's related to the question that you asked a bit earlier, Lan, right? How do you know now what player 1 will do? Well, player 1 takes this red stuff as given. So the equilibrium path here, we'll kind of go here. So player 1 will have the choice between getting an 8 if he goes on A2. He will get a 2 if he goes on A3, and he will get a 6 if he goes down A1. So what will be in the best interest for player 2? For player 1? A2. I highlight that. Those highlighting are effectively the pure strategies of each player. So what's going to be the subgame perfect Nash equilibria? What's going to be the subgame perfect Nash equilibria? Subgame perfect Nash equilibria will be a profile of strategies, so a pure strategy for each player. So it will be A2. Then for player 2 it will be B2, E2. For player 1, so I made a mistake for player 1, right? What should I have written for player 1? He goes twice, right? So it's A2, G1. A2, G3, sorry. And for player 3 is simply C2. That is your subgame perfect Nash equilibria. That is your subgame perfect Nash equilibria. This is the subgame perfect Nash equilibria outcome. This bit here is the outcome. And this bit here is the equilibrium path. how I get to that equilibrium. So the red dots are highlighting the strategies. They form the subgame perfect Nash equilibria. The yellow highlighting is the subgame perfect Nash equilibria outcome. The orange kind of highlighting is the equilibrium path. How do I get to that outcome? And this is how you do subgame perfect Nash equilibria. If you understood this, you'll realize that we made up this game, okay? We made it up. And I didn't even have to think about it, right? I kind of like went mechanically through it. So as long as you convince yourself that it's a mechanical process, that you can learn this process, that's the first step to do. And then you can think about what are the implications, what does this mean, etc., etc., etc.